Okay, so I put a short link here where you can see the exact instructions that will execute in the terminal now, but it's also part of the GitHub account for this workshop. So it directs you to the GitHub page, and then you can see the commands that you can just copy paste, and they will just work out of the box. So we will do now some exercises to set up Cocos or for theta, compile the Cocos library, and then we will look at the exercises and compile them, the first small exercises, and then also run them on a compute node. So the first thing that you should probably do now if you want to follow this live is, and I did this already, so in the file that you find there, it shows you instructions on how to get a login node, an interactive KNL node. So you just execute this qsub command and put the string here to get it for the workshop, and then you just load the Intel module and the GCC module, and then you are on an interactive KNL node. And I did this already in advance so that we don't have to wait for the allocation to go through. Okay, so let's start with building Cocos. So I'm just here in my home directory, and let's make a directory, and we can just pull the latest version from GitHub for Cocos. And all I've been doing here in the left terminal is now on the login node. So we build everything on the login node and then run it later on in an interactive node. So we put the latest master branch of Cocos, which should be fine just for running on theta here. So we are going to build with CMake, so we need a build directory. And the modules that we need to build Cocos for theta is Intel, GCC, and CMake. So we can just load these modules. And one thing that we have to do on a Cray machine is we have to set the link type to dynamic. So that's very important, otherwise you won't be able to run. So set the environment variable to dynamic. And then we are in our build directory here. And to build Cocos, we just execute the CMake command. So we point it to the Cocos project. We want to build in release, and then the compiler that we use on theta is just capital CC. And then we say we want to compile for KNL. So we set the arch KNL to on. And we actually want to build a library that we can later link against. So we set also an install directory, which is in the current working directory on my left terminal. And for KNL, we want to use the OpenMP backend. So that's host OpenMP code. And in case your application also uses the serial backend for serial task, we also turn the serial backend on. But the default execution space, if you don't specify any policy, any execution space in your policy, will be the OpenMP backend. And for my build, I turn off the unit tests just to make the build a little bit faster. But you can set the unit tests to on in case you want to verify that the machine, that the build works on theta. I already did this, and that should be fine in the way I set it up here. So let's just copy paste the CMake command. Okay. So it gives you the information that the host parallel execution space is OpenP. So the default execution space for host is also OpenP in this case. Now we're going to build with make -j. Okay, so that went through without any errors. And then the last step is just to do make install. And then the library is then installed in the path that I put into the install prefix, which is just my build directory /install. And for applications, or in particular for the exercise that we're going to look at, we're going to build them with CMake. And this requires me to set the CMake prefix path to the install directory of my Cocos build. So I will just copy paste that into my left terminal. And then when you have set up your application correctly with CMake to the Cocos module, it should then inherit all the compiler flags that have been set during this Cocos library build process, which is very convenient. So you don't even have to figure out what compiler flags you have to use for building your application. That's the recommended way to do this. Okay, so we have the library now. Let me move this bar a little bit away here. And now we are going to go back one directory and going to pull the Cocos exercises. So they're also part of a GitHub repository. And inside this GitHub repository that we just pulled, there's a lot of documentation in there. Also a lecture series, which I recommend. You can just go in there. It has a lot of PDF files and it describes everything that you need to know. But what we will do right now is we will focus on the exercises. So let's go into that directory. And you will see now here several exercises that you can do. They start very easy. So when you go to 0, 1, that's the easiest example that you can think of. And then when you go further, they get more complicated. But the nice thing of all these exercises, let's start with 0, 1 here. So they give you 2 directories per exercise. One is the begin, where they describe the problem that you are supposed to solve. And then if you get stuck or want to see if your solution makes sense from what the developers want you to do, you can also just go into the solution directory and see what the correct solution would be. So let's start with exercise 0, 1. And what we will see in each of these directories is you have one C++ file in this case, and a CMake file that we'll use to build. So let's first show how you can build these exercises. So if you're just inside this 0, 1 begin directory, you can just create another build directory. You go inside that build directory, and then the next or the last step that you have to do just to build this exercise is to do CMake ... to the directory in front of you. And then you just type make, and it builds the exercise for you. And note that we didn't have to specify any compilation flags. That was all done by the Cocos library that we already set up. Okay, so let's look at the particular example. So we're looking at the exercise 1. Okay, so when you go inside the exercise, you will find for each exercise in the beginning like a few comments which tell you what this exercise should achieve. And this, in particular, this exercise focuses on a vector product. So you have the operation, you multiply a matrix A with a vector X, and then do the dot product with a vector Y. And the task for this exercise is that you implement it using a Cocos parallel reduce. And then along the way, every time when you have to make changes to this code, they mark it as an exercise. For example, in this case here, you have to include the Cocos header file to get access to all the Cocos APIs. So in the way this exercise is set up is everything is set up to, it's written just in C++ and it works on the host and serial. So we have 3 pointers, X, Y, and A. And X and Y is a vector, A is a matrix. And then you initialize them on the host just with a scalar loop. And your exercise would be to convert this into a parallel execution using the Cocos parallel for construct. And you have to do this for X, Y, and A. And then the next step would be to actually look at the the vector product. So the kernel that we are looking at are these lines here. So we have an outer loop N, so it's a N by M matrix. And then we have an inner loop M, and it performs a reduction in the reduction variable. And this is all still in written on the host in scalar. So your task is also to convert this to a Cocos parallel construct, and since we are doing a reduction, it has to be a Cocos parallel 4. Okay, so let's open the solution for this. So note the first step was just to make it parallel, and everything is still on the host. And for KNL and also for CPUs in general, you have a shared memory space. So this exercise focuses only on parallelization, and that works fine on the CPU because you don't need to copy data from it to the device because there's no dedicated device memory that is not a shared memory space. So when you see on the left, we still had the host, just a host for loop scalar, and you transform it into a parallel 4. So you don't specify any execution policy. You just put your parallel 4, you give your parallel 4 loop a name, and you give how many iterations you have, and then you put a Cocos lambda, and then the operation that you want to do. So in this case, we initialize y to 1 for all the elements. And in this case, it would default to the default host execution space, which is OpenMP. So this would be parallelized over all the cores that you have on your machine. You do the same for X, and then the same for the matrix. And for the actual A times X times Y kernel, we have to use a parallel reduce. We put N as the outer dimension, and then we pass a Cocos lambda. We have to give a reduction variable, which Cocos uses then internally as the parameter here. And the way to pass then the reduction variable that you have on your host to this parallel reduce construct is by putting it as the last argument of the parallel reduce. Okay, so that's what you had to do for this exercise. So let's compile the solution and run it on the login node, the interactive node. So we go into the solution directory, create a build directory. And then we build the project. So it's built, and then we go to now to the interactive node. And we go into the directory where we have built. So we have now the executable 01 exercise, and that is what we want to execute now. And I gave you already the command how to run these exercises. Let me just copy paste that from the instructions that are on the GitHub and put them here. So we have to use AP run, and we pass -d, which says how many threads we want to use on this architecture. So in KNL, you have 64 cores, and each core has 4 hardware threads. So we put 256 threads that you want to use. and we want to have 4 hardware threads per core. And we want to run now the 0-1 exercise. Then we put n repeat, so we want to call the kernel 200 times to average our results, and then we put a matrix which is the size m times m, so it's 14 times 12. No, it's 2 to the power of 14 and 2 to the power of 12, which is the dimension. And then let's run that. So we have a 16K times 4K matrix. And then Cocos runs this exercise. And in the end, what we care about here for this kernel is the bandwidth that we can achieve. And it prints it out in this case. So in this case, it achieves 320 gigabytes per second. And that is, for this KNL machine here, the maximum that you can achieve with the MCD RAM that you have on the KNL, which is around 400 gigabytes per second, what you can achieve. Okay, now let's go to a more complicated example. We go to exercise 02. Okay, so remember in the first exercise, we only introduced parallel constructs from Cocos. So the next step is to make this code really portable to architectures where you don't have a shared memory space. And that goal of this exercise is now to introduce Kokkos Views. So this is what we had before. We had in the just a plain allocation on the host with bare pointers, and your exercise would be to replace all of those with a vector with a Kokkos view. And when you do that, you have to also change how the views are accessed. So you can't use these bracket operators anymore. And you have to do the same for the kernel. So let's look at the solution. So we introduced the Cocos view, and our data type is double. So we need a double pointer for the vectors, and we need a double star star for the matrix because we have 2 indices, and that's how we define our views. And then we just declare our vector, give it a name, and give it the dimension. And for the matrix, we have to pass 2 dimensions. And then when you initialize it, remember, this is still all on the host. We haven't done any data transfers yet explicitly. And this is only supposed to work if you, or in this case, if you have a shared memory space, if you don't use anything related to managed pointers. So we have to change how y is accessed. So we just changed it to from this bracket to the other one. And we do this for y, x, and also the matrix. And we haven't specified any execution space or memory space yet. So this is all going to the default one, which is OpenMP. And you have to apply the same change also for the kernel. So change how you access your views. Okay, so how much time do we have left?
There's about 6 minutes until the next break.
Okay, then let me go to the final exercise that I wanted to show, which is a little bit more interesting because we can look at some performance numbers there. So we want to look at a version of the same problem where we already have introduced how we transfer data from the host to the device. So what should have been done in the exercise 3 is you introduce so-called host mirrors, which you then can later use to copy data if your architecture needs it from the host to the device, and that can be done with these deep copy calls. But in this exercise 4, we have been also a little bit more explicit. So we defined what is if it's a row or column major order, and that can be done by specifying the Cocos layout left or layout right. And we can also specify the memory space, and you can play around with that later in case you want to run on the Theta GPU. You can use the CUDA space, but in this case, what I will show now is just still all the host space, which is OpenP space. But let's take this example, compiled and run it on the interactive node and see what performance we get. So let's build it. Okay, so it's built, and now let's run the exercise 4 and see what performance we get. Okay, you have all been able to see that it's very slow, so you only get 10 gigabytes per second. And the reason for that is that we have been too explicit. So we have defined what the order of the view should be. But the layout that we chose here is only good for SPMD programming languages. And for OpenP on the CPU, that's not SPMD. So you don't want to use Cocos layout left. Instead, you want to use Cocos layout right, which changes which index is the fastest. So let's recompile the application. And rerun it. And then you can see that we are back to our maximum bandwidth that we can achieve here. So it's 330 gigabytes per second. And just to make my last point here to why that impacts the performance. Oh boy, what's going on here? So if you look at just the kernel, when we go from Cocos layout right to layout left, we change if J is the fastest or I is the fastest. And for the CPU here, you want the innermost loop to be the one which is the fastest. So I should be your fast index in this case. And when we had layout left, J wasn't the fastest. And that gives you bad performance. And the last thing that I had here in my steps that I gave you in the GitHub repository, there's one tool provided by Argonne to show you how this AP run tool works, to show you how many cores you use or how your affinity is when you use MPI and OpenP. So I put just the link here, how to compile it and how to run it. So if you have problems figuring out what AP run does, just follow these steps and it will show you what you have to do. All right, okay, so that's all that I had.